Dear students, I would like to share with you a few lessons that on the topics that we have discussed after the basic portion of the Fortran, the simple things that we have already discussed before the mid-sem, and we have also done problems on it. So first I would like to start with Euler integration, though we have done a lot of problems on it before the mid-sem and before the uh, classes stopped and you had to go home, but still I have seen over the teams meeting that I had in the last 2 months, I have seen that some people still have some problems on that. So I will begin with that. So numerical integration. Euler mechanism is the smallest, is the simplest kind of numerical integration method. There are other methods like Newton-Raphson, etc., which I am not going into, Newton's method, etc., which I am not going into the details. So when I go into the Euler mechanism, what we are saying is, suppose we have du dt is equal to some function of u. It could be u, it could be bu square, or it could be u e to the power u square, au e to the power bu square, etc. It could be any function of u, right? Single variable. In that case, how do we integrate? We integrate analytically. U is equal to integration fu dt. But always this is not possible because we don't know how u is a function of t. But let us take, for example, the first order kinetics. Then we have dA dt, which I can write as dA dt is equal to minus k1a. And we know a as a function of time will give us exponential decay because a is equal to a0 e to the power minus k1t, right? So it will begin from a0 and it will want to go to a is equal to 0, right? Now for a simple problem like this is the analytical solution, but how do we numerically integrate it? So I could write delta A by delta t. So dA over dt, I am approximating it to be equal to delta A over delta t when delta t I can say tends to 0, or delta t is very small, right? How do we define? We can define differentiation as limit delta t tends to 0, delta A over delta t is equal to dA dt. That is the definition we already know. So as delta t tends to 0 or delta t is small, right? So now if we write that, and let's say that is equal to minus k1a, then at t equal to 0 we have a is equal to a0. At t equal to 1, let us say a1, okay? Then what do we have? a1 minus a0 over t1 minus t0 is equal to minus k1 a0. So a1 is equal to minus k1 a0, right? So a0 goes here, a0 minus k1 a0 into delta t, okay, whatever is delta t, or t1 minus t0. So this is how for a general function. So generally a t plus delta t is equal to at minus k1 a t into delta t. For a general equation that we started, dA dt is equal to f of a. What do we have? We have a t plus delta t is equal to at plus. So we are going to take this function over here, f of a into dt, right? So that is what we have. So this is the general formula. So for this, once you have a0, then from there you can find a1, then you can find a2, a3, and so on and so forth. Now in this formula, so what am I doing? If you try to understand what is being done, actually you can look at it geometrically. So this is my, let's say this is my concentration, right? Time and a, this is a0, say. So what are we doing? At any point delta t, so let's say these are our delta t's, I can consider a point here. So if I zoom this part, if we zoom this part over here, we will be able to show that so instead of going from here to here, so this is, let us remove this. So this is the slope, okay? Slope dA dt or f of a. So we will have a of t plus delta t, a of t. A of t plus delta t is equal to at plus fa into this is delta t. Okay. So what do we have? So a of t, so is let us call this L, let's call this O, let us call this P, Q, R. So we will have a of t plus delta t is OQ. Fa, what is the slope? Into What is the slope of the line at A, right? So slope of the line could be said to be tan of theta. Slope is equal to tan theta, which is equal to PQ. So you realize, right? Why are we writing this definition? AT plus delta t is equal to AT plus FA into delta t, because FA is the slope, which is equal to tan theta over PQ by QR. Now the only problem here that you see is, this is the line that I am numerically getting, and this is the exact value. So whether I go from here to here, or I decide to go from, so depending on, so what is the slope here? So this is the slope here. You see the problem? This is where we want to go, but this is not the slope at DA. This is the, let me just draw this for you once again. You will see the difference. So we have this as the line. What is the slope at? This is the slope. So if I want to go, if this is my delta t, so I am actually going to come, so this would be my slope at A0. This line is actually going to give my f of A into so this point will actually be our A of t plus delta t is equal to AT plus f of A into delta t, instead of the actual point at here. But now if I don't go delta t that amount, but I decide to take this area and I make it larger, okay, and I take this area and I make it larger, and I tell you, let us take, instead of making this delta t, I am going to make smaller delta t. Let us divide it into two parts. Let this be my delta t prime. So I am choosing delta t's which are smaller now. So instead of going there, I will come here to this point. My second point will, sorry about that, my second point will take the slope here and will go there, and my third point will take a point here and will go there. So from here originally, so from originally, I'm just going to explain to you what I'm getting. From original point here, what we are now getting is so what we are now getting is from this point, if you take, so this is my first point, so this is my at plus delta t prime. From here, if we take the slope again, we reach somewhere here, a t plus delta t twice delta t prime, and from here we take the slope once again, and we are somewhere closer, a t plus thrice delta t prime. So we had to take 3 different steps to reach a point which is much closer than where we were before over here. So you see, this was the original a t plus delta t, where delta t is equal to 3 times delta t prime, right? So we decided to bring down our delta t 3 to 1/3 of the original value of delta t, which was original delta t, and now we make it 1/3, and we are in a value which is much closer to our actual black point than we were at this red point. So the step size in this case is very important. So this delta t value, so we have at is equal to at plus delta t plus whatever is a function of a into delta t. So this delta t value is very important, or the step size. Smaller the step size, we are closer to the exact solution. But then when you are doing a numerical integration, suppose I want to integrate for at between 1 to 100. So I can take delta t is equal to 10, then I have 10 points only. I can take delta t is equal to, or let's say from 0 to 100, I want to take delta t is equal to 1. So number of points will become 100. When this becomes 0.1, this becomes 1000. So as we are reducing the step size and increasing the exactness of our solution, what is happening in the other hand is our number of points, or the number of times we have to run the simulation, is increasing. So we can just start, so there has to be a balance. So if for solutions like this, first order reactions, second order reactions, we already know what is the analytical solution, the exact solution. We can change our delta t values and see which is the value which gives us the best solution. And then we need not actually go for higher values. We need not make the step sizes lower and lower. We can strike a balance. But for problems where we don't exactly know, for example, later on with the Euler's method, I asked you to do the Runge-Kutta method, right? The ozone problem, where there are several equations. Let us not go to the ozone problem. Let us take the simple A gives B gives C, this consecutive reaction. That's something I had asked you to do, because that has a beautiful, we know how it should look like. So A will decay depending on the K2 value. This is A. Depending on the value of K2, the B could either increase so much and decay, or it could just decay, and the C value would again slowly increase, right? So this is the value of C. So in this way you can actually find the analytical solutions by, so these are the concentrations and this is time. So you can actually find what is the different concentrations and what are the different times analytically. But now numerically what you can do is you can just take all of them. But one thing you have to remember here, as your A increases, for example at T, okay, this is our T and these are are values of a, b and c. Okay, so we have a, b, c. Let's say it's a0, b0, c0 at t. At t plus delta t, our a's changes, right? It becomes a, so I'm sorry, this was 0. So it's just a at delta t, b at delta t, c at delta t. So for a particular point, as you are running your program, all three should be simultaneously calculated. I am telling you what I mean. What we mean is dA dt is equal to minus k1a, dB dt is equal to k1a minus k2b, and dC dt is equal to k2b. As we are running the while loop or the do loop, so as we are doing the do loop, I goes from 1 to whatever, let's say 1000, and step sizes are defined beforehand. So in this case, we are going to do a is equal to a plus, so instead of writing plus, our function here is minus k1a, b is equal to k1a minus k2b. So okay, so this is b. What is a is equal to a minus k1a into delta t, whatever is your delta t. We oftentimes write delta t as h as the step size, but it is any name that you want to give, it doesn't really matter, but mostly keep it between delta t and h to make things simpler. So b is equal to not a plus, b is changing from b. If I take this equation and we try to get the b from there, b is equal to b plus k1a minus k2b dt, and c is equal to, from here, c plus k2b into dt, and then you do your stuff and then undo. So for the time loop, so at every time all three of these has to be integrated at the same time. Okay, so that is one important thing. Those are the mistakes that many people are making. Now coming to, so as I said, between 2 points, this and this, when I go take a step, we are still going from here to here. What would be a better method? One is to reduce the step size. We can reduce our step sizes. There is another method to go about. If I don't take only the slope here, but I take the slope here and the slope in between. So the slope at delta t, the slope at t, at the initial point t, the slope at t plus delta t, and the slopes at t plus delta t by 2, that is half of, in between. So that is what gives us the Runge-Kutta methods. So specifically we mostly use the RK4 method. So how do we define it? Generally we were saying a is equal to a plus f of a into dt, right? So now instead of going that far, what we are doing, we are taking a step in between, and I'm going to tell you what that is. Okay, so